Okay, I'm going to have a crack at doing test 1 for PHYS1021 and see how I go. I'll start with the multiple choice. Okay, the mass number of a nucleus is the number of neutrons, protons, electrons, protons and neutrons, because they have roughly the same mass, and it counts the total mass numbers, the total number of nucleons, protons and neutrons. Okay, so a few isotopes of uranium are 234, 236, 238, where that is the mass number. The one with the most neutrons, okay, it's going to be that one. So how many neutrons? Well, the total number of nucleons is 238. Take away 92 is 146. Okay, so that's the answer. Oh, when a particular isotope emits an alpha particle, what new element results? Well, an alpha particle it's got a mass of 4 and a charge of 2. So when that goes, we're going to lose 2 from here, 2 from the atomic number and 4 from the mass number. So the atomic number decreased by 2, mass number decreased by, atomic mass decreased by 4. Okay, a certain radioactive element has a half-life of an hour. If you start with 1 gram at noon, how many will be left at 4 p.m? So at 1 p.m. you'll have a half, at 2 p.m. a quarter, at 3 p.m. an eighth, at 4 p.m. 1/16 of a gram. So calculator, 1/16, 0.0625, close enough to 0.063. Which of the following is most penetrating in common materials? Oh dear, I don't know. I'm guessing. I'm gonna guess gamma. The chain reaction that occurs in fission is a build-up of, well, it's neutrons, because each atom decays when each nucleus decays when it absorbs a neutron, and then when it decays it emits more neutrons, and so there's a rapidly escalating number of neutrons. Okay, the greater the surface area for a given mass of uranium, the less likely, more likely, neither, none of these. It's actually the less likely, because the surface area allows, greater surface area gives a neutron a greater chance to escape before it causes another nucleus to become unstable and decay. So if you increase the surface area, it means it's less likely. Radiation from a point source obeys an inverse square law. If a Geiger counter 1 meter from a small sample registers 360 counts, what rate the rate at 3 meters will be? So basically it goes as 1 over the distance squared. So that is 1 over, at 1 meter, that goes to 360. So 1 over 3 squared will be 1/9. 1/9 of that, 360 over 9, which is going to be equal to 40. 40 counts. And we have magnetic resonance imaging involves X-rays, gamma rays, neither of the above. Neither of the above. It involves using strong magnetic fields to interact with the magnetic moment of the nuclei. It's not bombarding it with radiation at all. On to mechanics. Alex, mass 75 kilograms, is standing on bathroom scales in an elevator which is moving upwards with a constant speed of 10 meters per second. What is the net force on these scales? Okay, the scales are moving at a constant speed, therefore the net force on them is 0. There's lots of forces on them, but the net force determines their acceleration. We say constant speed, so there's no acceleration, so therefore the net force is 0. the net force is the sum of all the forces. Here we have a bullet is dropped into a river from a very high bridge. At the same time, another bullet is fired from a gun straight down towards the water. Neglecting air resistance, the acceleration just before striking the water is blah blah blah. It's the same. Okay? Neglecting air resistance, it is the same. Because the acceleration that anybody feels in free fall is 10 meters per second squared. So it's the same. They're both in free fall. Okay. You observe two balls of identical shape, size and surface characteristics being dropped from rest at the same time and height. Shortly after their release, the balls are seen to be falling with different speeds. Which of the following statements is incorrect? Okay. Well, they're identical, except possibly for their mass. But they fall at different speeds, so the mass of the balls must be different, because if the masses were the same, they would be totally identical and they would fall with the same speeds. The balls experience air resistance, and the air resistance acting on the faster ball is smaller. That's actually dodgy, because as you go faster, air resistance increases. So in all likelihood, the faster ball is actually the heavier one, and what we need is for the heavier ball who has greater gravitational force and also greater air resistance. So we're going to say that that is probably wrong. The balls are not in free fall. That's true, because otherwise they'd fall at the same rate. The balls hit the ground with different velocities. Well, it seems highly likely given they're travelling at different rates. Both balls experience a different force due to air drag. Well, they actually must, because if they experience the same force due to air drag, then yeah. So it's B. We'll go with B. Okay. Ball A is dropped from the top of the building. 1 second later, ball B is dropped from the same building. Neglect air resistance. As time progresses, the difference in their speeds increases, decreases, stays the same. Well, let's say ball A has reached 10 meters per second when we drop ball B. In the next second, it will increase its speed by another 10 meters per second to 20 meters per second. Ball B, which was doing 0 meters per second, it will increase its speed to 10 meters per second. In the next second, this one will go up to 30 meters per second, and this one will go up to 20 meters per second. So it looks to me as though, since they're both increasing by the same amount each second, that the speed difference stays the same. Now, I put this question in myself, didn't get it from anywhere, made it up. And the reason I did it is, this is a sort of nasty question they put in the GAMSAT, okay? This is not an easy question to do. So let's read it and see. An object experiences a constant net force in the plus x direction for 2 seconds and then experiences no net force for 2 seconds. Assuming the object started at rest, which of the following graphs, each covering the whole 4 seconds of motion, best shows the object's velocity as a function of its distance from its starting point? You'll notice it's distance. Usually everything is velocity versus time, distance versus time, but this is velocity versus distance. Okay? The first thing to do is to say, well, they all have a bit at the top where you can see the velocity is constant, and that's because there's no net force. Alright? What speed are they doing there? They're doing 4 meters a second. In each of the 4 meters a second. How long do they do 4 meters per second? That's for 2 seconds. So the distance they'll cover is 4 meters per second times 2 seconds equals 8 meters. So in this flat section they should cover 8 meters. Now this one they cover 4 meters. This one, they cover 6 meters. This one, they cover 6 meters. These two here, they both cover 8 meters in that time. So it's between B and E. They're our choices. The rules in multiple choice tests are if you're in a hurry, you now guess. Okay? So we won't though. Alright, let's ask a question. It's either linear like that, which has velocity proportional to position, or it's something curved like that. We know that V equals AT is the formula that tells us how it would look with respect to time. So we could use that, but it's tricky because this is distance. I know. Look at this one. This one says that at a distance of 2 meters, it's doing 2 meters a second. Okay? Let's see if that's true. Okay? So how long does it take to get to 2 meters per second? Well, we can see that after 2 seconds it's doing 4 meters per second. So its acceleration is 2 meters per second squared. Okay? So therefore we can say its velocity will be 2 at t equals 1 second. 1 second is how long it will take to get from 0 to 2 meters per second. So t equals 1 second. And now we can say, okay, so what's the distance then? Well, the distance is a half at squared, which is a half times 2 times 1, which is just 1 meter. So what we're saying is that when it has travelled, when it is doing 2 meters a second, it should have travelled 1 meter. Now this one shows that when it's doing 2 meters per second, it's travelled 2 meters. This one looks much more reasonable. So therefore the answer is E. Okay. An object experiences constant non-zero net force in the plus x direction. Which one or more of the following could represent the graph of its x position versus time? Okay, so this one is constant velocity, so it's not that because it's experiencing acceleration. This one looks pretty positive because it starts off and then it's gradually increasing the rate at which its x position is changing, so that one looks good. This one looks bad, it's going the wrong way. This one looks bad, it starts off going in the plus x direction, but then it's slowing down. The rate at which its position is increasing with time is reducing and finally going negative. So that's no good. This one, it starts off moving in the negative x direction, but it's gradually slowing until it's hit 0, and then it's moving in the positive x direction and it's gradually getting faster. So this one is okay. So this one is motion that went whoop. This one is just motion that went whoop. And so these two are good, A and D. Another slightly harder question. Alright. So hopefully we're going good time-wise. At 14 minutes, that's about right. Okay. Alright. We want to divide them into groups that have the same number of neutrons. Well, that has no neutrons, so 1H1. This has 1 neutron, 1H2. This has 2 neutrons, 1H3. This has 2 protons and 1 neutron, so that's 2He3. And this one has 2 protons and 2 neutrons, 2He4. So there we are, 0, 1, 2. Okay, divide them into the groups that have similar chemical properties. Chemical properties only depend on this number here. So it's simply 1H1, 1H2, 1H3, and 2 helium-3 and 2 helium-4. That's easy. Okay. Now, one long, complicated calculation. I can feel myself going to sleep already. Okay. We've got atomic mass of lead is that. What is the average binding energy per nucleon in million electron volts per nucleon? Okay. So, alright. The binding energy is the difference between the sum of all the component parts and the actual mass. Alright, because the actual mass is always slightly less than the sum of all the component parts. So we got to add up the component parts. So that's 82 times 1.007276 U plus neutrons. How many neutrons? Well, there's 82 protons, 208 altogether. I'm going to be lazy. 208 minus 82 equals 126. 126 times 1.008665. Now, we need to add to that 82 electrons, because when we subtract away the atomic mass, that includes the electrons. So it's 82 times 0.000548858 U. And from that we need to subtract 207.9766 U. And I'm going to do that, and I'm going to get, okay, one long calculation. 82 times 1.007276 plus 126 times 1.008665 plus 82 times 0.0054858 equals minus 207.9766 equals, okay, I get 1.7568 mu U. And now I need to convert this to energy. Okay, so this is equal to, I've got to convert it to kilograms, so this is equal to times that by 1.66054 done at minus 27 equals, I get 2.917 by 10 to the minus 27, and then I've got to times it by c squared. Therefore energy equals times 3 exponent 8x squared equals 2.6255 by 10 to the minus 10 joules. Okay, now now 1 electron volt equals 1.6 by 10 to the minus 19 joules. So therefore, if I want to take that, if I divide it by this, that'll give me the number of electron volts. So divide it by 1.6 exponent minus 19. Okay, and we get energy equals 164. Let's just look at this. So that's 10 to 1, 10 to 2, 10 to 3, 10 to 4, 10 to 5, 10 to 6, 10 to 7, 10 to 8, 10 to 9, 1.64 by 10 to the 9 electron volts. Okay, nearly there. Now, And that's for the whole thing. It says per nucleon, so I've got to divide it by the number of nucleons, 208. So I now get energy per nucleon equals 7.889 by 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6. So I get 7.89 by 10 to the 6. No, get rid of the 10 to the 6 because I'm going to call it mega electron volts. That's electron volts. Alright, that's the answer. That was hard work. Okay. So that's just a straight out grind. You just do it and you're done. Okay. In uranium-lead dating, one of the clocks used is that decay. Write down the decay equation in appropriate notation with the unknown number of alpha particles represented by X and the unknown number of beta particles represented by Y. How many are involved in the process? Okay, so we start off, we have 92U235 goes to 82PB207, and they say we have X alpha particles, that's 2He4, plus Y beta particles. They are, how do they work? They have a charge of -1 and a nucleon number of 0. So here's our equation, alright? And what we need to do is we need to balance it, okay? Just like in chemistry you balance equations, so you have to balance this. And what we need is we need the number of nucleons on both sides to be the same, and we need the total charge on both sides to be the same, okay? So firstly the nucleons, okay? We can see there's 235 and 207, so 235 take 207 is 28. So we've got 4 here and 0 there, so it doesn't matter how many of these we have, they won't add any nucleons. So therefore, if we've got 4 there, 7 4s will give us 28 of those. So we can now write that as 7, okay? 7. Alright, now charge, okay? We've got 92 here, 82 here, 7 2s are 14 here. So if we look at this, 82 plus 14 here gives us 96, but we only started with 92, so we need 4 of these -1s here, 4 electrons to take away the excess charge. So that becomes 4. And we're done. Apparently, I haven't looked at the marked papers, but apparently that one wasn't done so well. I don't know. Then the easy one. A radionuclide has a half-life of 3 days. Its decay products are not radioactive. After 6 days, find the ratio of the count rate to the original count rate. Okay, well, half-life, half of it is left, and the amount of activity is proportional to the amount of substance that is there. So if after one half-life it's gone down to half of its original, after 2 half-life it's gone down to quarter of its original, and 6 days is 2 half-lives. Now we come to my favourite questions. Now all of these are basically using 3 simple formulas, so let's do them. What's the acceleration of the 2 masses? Well, okay, 2 kilogram, 3 kilogram, horizontal, frictionless, a net force of 8 Newton is applied. A equals the sum of the forces divided by the mass is equal to 8 over total mass that it's pushing. That 8 Newton mass is accelerating 5 kilograms, so it's 1.6 meters per second squared. How far do they move in the first second? Well, distance is a half AT squared is a half times 1.6 times 1 squared, which is 0.8 meters. How long must the force be applied for the masses to reach 4.8 meters per second? Well, they get faster by 1.6 meters per second every second, and so 1 second 1.6, 2 seconds 3.2, 3 seconds 4.8, so it's 3 seconds. Or, if you want, V equals AT, therefore T equals V over A equals 4.8 over 1.6 equals 3 seconds. And now the slightly harder question. What is the magnitude and direction of the force that the 2 kilogram mass exerts on the 3 kilogram mass? Well, if you look at the 3 kilogram mass, it only has one force exerted on it, and that is the force exerted by the 2 kilogram mass. Okay, so our 3 kilogram mass has acceleration equals F over m. Therefore, we write that F equals ma equals 3 kilograms times its acceleration, 1.6. Therefore, 3 times 1.6 equals, it has a force on it of 4.8 newtons. And since it's accelerating to the right, Okay. Just going back, this is a key thing about Newton's laws. If you know this acceleration of this mass, you can work out the net force on it. And we know that the force only comes from one thing, so therefore the net force is being exerted by the 2 kilogram mass. Okay. A ball is to be rolled down an inclined plane from rest, and the time it takes to cover 2 meters recorded. The acceleration of the ball is known to be 0.1 meters per second squared. How long does it take the ball to reach the 2 meter mark? Well, we know d equals half at squared, so rearranging we get t squared equals 2d over a. Therefore t equals the square root of 2d over a equals the square root of 2 times 2 over 0.1, and calculator, square root brackets 2 times 2 divide 0.1 close bracket equals 6.32 seconds. Okay, what is the speed? V equals AT. It started from rest, so that's equal to 0.1 times 6.32, which is equal to 0.632 meters per second. Alright, in a less successful version of the experiment in the previous question, the person releasing the ball accidentally gives it a nudge up the slope so that its initial speed is 1 centimeter per second up the slope. How much time does the ball spend moving up the slope before it stops and starts rolling down the slope again? So it goes up and turns around and comes back down. Okay, and its initial speed is equal to 1 centimeter per second, which is equal to 0.01 meters per second. Okay, so the time it takes to slow to a stop from 0.01 meters per second will be exactly the same time as the time it takes to go from rest to that speed. If you picture it, it rolls up, slowing, turns down, turns around and comes back down and reaches the same speed again. It'll take the same time to go up as it takes to go down. So we can just say V equals AT, rearrange T equals V on A equals 0.01 over 0.1, and we get 0.1 second. So it takes 0.1 second to go up to there, another 0.1 to come back down again. How far up the slope does it move in this time? far too many d equals a half at squareds in this. .0005 meters, which, if you like, is 0.5 millimeters. In other words, it doesn't move very far up the slope at all. Okay. And lastly, one from the practice class, or no, second lastly. First, a 2 kilogram box sits on a level frictionless surface and acted on by 10 Newton force to the right. What is the acceleration of the box? A equals F over m equals 10 over 2 equals 5 meters per second squared. Done. Now, instead of the 10 Newton force, we're now going to attach a 1 kilogram mass. Okay, and it goes over a pulley like so. What's the acceleration of the 2 kilogram box? Now here the thing is, all of our force is mg from there, which is equal to 10 newtons. But the 10 newtons is no longer just accelerating the 2 kilogram box, it's also accelerating the 1 kilogram mass. So therefore, the acceleration equals F over m now is equal to 10 newtons over 3 kilograms, which is 3.33 meters per second squared. And lastly, what is the upward force exerted by the string on the 1 kilogram mass? So let's just look at the 1 kilogram mass in isolation. There it is. Okay, it has two forces acting on it. It has the tension in the string acting upwards, and it has mg, gravity, acting downwards. And we know that its acceleration is equal to 3.33 meters per second squared. So therefore we know that force equals ma must be equal to 3.33 newtons, and it must be acting downwards. But we know that the force of gravity here is 10 newtons acting downwards, and we know that net force acting downwards is just 3.33 newtons. So therefore the tension acting upwards must be 6.67 newtons acting upwards, so that the net force gives us the acceleration that we know it has. And we're done.